Hello, please turn to page 10 in our Relations and Functions packet. In our previous unit, Linear Equations, you learned that a linear equation has a constant rate of change and is represented in a graph by a straight line. Because any straight line on a graph, with the exception of a vertical line, meets the requirements of a function using the vertical line test, we refer to linear equations as linear functions. So let's start with the graphs. It says that if a graph shows a single straight line, it is linear. Otherwise, it's nonlinear. And this has probably been pointed out to you before. The word linear actually has the word line in it. We don't pronounce it liner, though. We say linear. So when I'm looking at this, I can see that the first graph has a line. So it passed the vertical line test. We call it a function, and it is a line. So this is a linear function. This next graph we can see would pass the vertical line test, so it's a function. However, because of the curve, it is not linear. So this is a non-linear function. So it is still a function, it's just non-linear. It's not a straight line, so it is a non-linear function. And our third, even though we see three separate straight lines, so to speak, it does not pass the vertical line test because we can touch the graph figured in more than one place, so this is just not a function. All right, let's move on to the tables. Tables represent a linear function if the rate of change, known as the slope or the unit rate or the change in y over the change in x, is constant or the same throughout the table. Conversely, if it's not constant, then it's non-linear. So let's look at this first table. We're going to start and we're going to check each one of these pairs for change in y over the change in x. So I'm going to start with y, and if I go from 7 to 9, I'm adding 2, so the change is 2. From negative 2 to 1 to negative 1, I'm adding 1, so this is 2 over 1. Our first pair is 2 over 1. Now going from the second ordered pair to the third ordered pair, from 9 to 11 is 2. We're going up 2, we're adding 2. From negative 1 to 0 is also adding 1. So we have 2 over 1. So far it's constant. We're going to go on from the third ordered pair, the third ordered pair to the fourth ordered pair. And again, we're adding 2. And on the x side, we're adding 1. So that's 2 over 1. And our very last set from 13 to 14 is adding 2. And from 1 to 2 is adding 1. So this is a constant rate of change. And so this is a linear function. So now let's test out our second table. We're looking for the change in our y values over the change in our x values. So let's look at our first change. From 9 to 0 would be subtracting 9. So we're going to write that as negative 9, or going down 9. From negative 3 to 0, that's going up 3. So negative 9 over positive 3, we can look at that as division, and so that value would be negative 3. Now we're going to try the second pair. We're going to go from 0 to 9, so we're going up 9, so we're adding 9, and from 0 to 3, we're going up 3. So our change is positive 9 over positive 3. But that would reduce to positive 3. So even though they look similar, they're not the same. It's not the same constant rate of change. Therefore, we can say that this is non-linear. However, it might be a function. So let's check back, and using what we know for a function, we're looking to see that every x value has one unique y value, and I don't see any of the x values. They're all different. And so every one of those x values has only one y value, so this is a nonlinear function. All right, so let's try the third one. As we check through this, once again, we're going to start with the change in y over the change in x. We're trying to see if it's linear. So if I go from my first y value to my second y value, we're going up 1. And from 9 to 4, we're going down 5. So we have a change of 1 over, we're going to write minus 5 is negative 5. So that's our first change. So now we're going to go from negative 2 to 0, and that's going up 2. And we're going to go from 4 to 0, and that's going down 4. So we have 2 over negative 4. Again, we can already see that these are not the same. So if I reduce 2 over negative 4, that would be negative 1/2, and it's not the same as negative 1/5. So this is nonlinear, but not only is it nonlinear, it might not even be a function. So we're going to check to see if our x values have more than one y value. And I can see doubles. I see 9. Well, this 9 is paired with negative 3, and this 9 is paired with positive 3. So already I can tell it's not a function. Then it happens again. This 4 is paired with negative 2. This 4 is paired with positive 2. So this is not a function. Now, is it not linear? It's not a function. All right, so let's move forward to equations. So please move on to page 11 if you haven't, and let's read what it says. Equations. In order for an equation to be linear, x can only be raised to the power of 1 or to 0. In other words, there are no exponents on the variable. A linear equation is generally written in the form of y equals mx plus b, also known as the slope-intercept form. And finally, the variable x cannot appear in the denominator, but can appear in the numerator. So because we haven't spent any time yet with exponents, just like if I had the variable x when we're combining like terms, I could put a coefficient of 1 with it, and it doesn't change the value. Well, the same thing happens with exponents. If I have x, I can write an exponent of 1, because the exponent tells me how many times I'm multiplying the base number of x times itself, and so it's going to appear just once. So it's going to keep its same value. So that's why when you see this first equation, we can say that x is raised to the first power. But that would be a pain if we had to write it every time, just like when we use x or y or a variable by itself. We don't always put the coefficient of 1. We only put it there if we need it. All right, so let's move forward. Let's go ahead and check out what we see. Y equals 5x plus 2. Well, that is a classic example of the slope-intercept form. Slope, in this case, would be 5. The intercept, in this case, would be 2, and those are linear. So this is a linear equation, but it's also a linear function. If we go on to the next one, we can see that there's an x raised to the first power, but there's also an x raised to the second power. So this is immediately nonlinear. This is also a function. If you recall, we talked about that x can be raised to a power, but we cannot have, or x can be squared, but we can't have y squared when we're talking about functions. When we look at this next equation, it's set up at the top. It said that x cannot appear in the denominator. And right here, we see x in the denominator. So this is this is nonlinear. Whoops. When I look at the next example, I see x, I see y. This is kind of standard form. While this is called slope-intercept form, we have the x and y on the same side. We refer to this as standard form. I can see x is not raised to a power, so it would be considered exponent of 1. So this is a linear function. And in lessons coming up, we're going to talk about how we can convert this into slope-intercept form to be able to use it more efficiently when we're graphing. That's linear function. And let's look at our last two. If you recall, it said that it's okay to have x in the numerator but not the denominator, so this would be a linear function. And then finally, the last equation, x is raised to the exponent of 3. It can only be 0 or 1, so this is nonlinear. And this would be a function, but it's just not nonlinear. Okay, thanks for taking great notes. We'll see you again next lesson.